Okay, we are going to look at 931 today. We are still going to be using our knowledge of inequalities, but now we are moving into two variable inequalities. So this is more what I would consider Algebra 1 level content. So read along with me in the introduction. It says, in section 9.2, you learned how to use an inequality with one variable to help solve a word problem. You also discovered that one variable inequalities can have 0, 1, or infinitely many solutions that can be represented on a number line. Okay, but what if the inequality has two variables? Usually it's going to be an x and a y. So first we are going to look at what the solutions of a linear equation look like. Okay, we've been working with equations, equal signs this entire year. So it says, let's go ahead and graph y equals negative 2x plus 3. You were actually asked to do this on problem 61 of your homework, but if you need a little refresher, let's do so right now. So when we're in y equals mx plus b form, we see that our b is 3, so that is our y-intercept. So put a point on 3 at your y-intercept, and then it looks like the slope is negative 2, so we're going to go down 2 boxes, over to the right 1, down 2, over to the right 1, down 2, over 1. Okay, then we take our straight edge. I'm going to try to use my line tool, and we are going to make a line that goes through the points. That worked out pretty nicely. Okay, so there is our line. Oh, and I can extend it. Okay, now from here, it says, is the point negative 1, 5 a solution to the equation? Now, what do we know about solutions? Okay, well, solutions, actually I'm going to type. Okay, we know that solutions make a mathematical statement true. Okay, that is something that we need to know for any problem we're approaching. So if we look and we say, how can we tell if negative 1, 5 is a solution on the graph? Let's find where that point is. Okay, so if I go back on the x-axis to negative 1 and then I go up 5 and put a point there, you can see that my purple point lands on the line. So on a graph, if the point lands on the line that you graphed, it is a solution. Okay, so we can say that on a graph, let's change our color here. So on a graph, a point is a solution if it falls, is a solution to the equation if it falls on, capitalize that, underline it, the line. So we can see that the point negative 1, 5 is indeed a solution based on the graph. Okay, and you can see my point, whoops, it got a little small, but we can regraph that at negative 1, 5. Okay, now how do we tell in the equation? Okay, in the equation we actually have to plug it in and kind of see what happens. So we are going to ask ourselves, question mark, let's replace y with 5. Is 5 equal to negative 2, replace x with negative 1, plus 3? Okay, now we're going to show the math. So is 5, I have my question mark, negative 2 times negative 1 is 2, plus 3. Well, 2 plus 3, 5 equals 5. So is that true? Does it make the mathematical statement true? Yes. So we can say that negative 1, 5 is a solution. SOL in math usually stands for solution. Okay, so why don't you try it? Okay, why don't you pause me and determine if 2, -1 is a solution to the equation, and what about the point 0, 0? Okay, and then go ahead and start me again and we'll check your answers. Okay, so for 2, -1, if I go ahead and get my point tool, let's go ahead and look at where that falls on the graph. So I'm going to go to the right 2, and I'm going to go down 1. And it looks like that point falls on the line, but sometimes when we graph by hand, it's not always completely accurate. So with the equation I'm going to plug in, I'm going to ask, question mark is -1 equal to -2 times, plug in 2 for x, plus 3. Is -1 equal to -4 plus 3? What's -4 plus 3? It is -1, so yes. So this first point is a solution. Okay, now let's look at 0, 0. If I find the point 0, 0 on the graph, that's the origin, and it doesn't look like the line goes through the origin. So my answer right away is I'm almost certain that it's not a solution, but we can go ahead and check, and we can say question mark is 0 equal to -2 times 0 plus 3. Well, I love multiplying by 0 because it crosses out the term. 0 equal 3. Nope, not a solution. Okay, so that is how you check using an equation and using the graph. So the moral of the story that we already kind of typed up here is, what determines if a point lies on the line? What is the difference between points on the line and points not on the line? Okay, well, we can go ahead and say all points on the line are solutions to the equation. Okay, in other words, they make the equation true. We can say all points not on the line are not solutions and make the equation false. Okay, where's my exclamation point? There we are. That's a key idea. All points on the line are solutions to the equation. They make the equation true. But all points that are not on the line make the equation false. Now, I want to stress that we're working with an equation right now. We don't have anything to do with greater than or less than symbols. Okay, but now we're going to introduce the greater than and less than symbols. On 66, it says, okay, in problem 65, we found that points on the line are the only points that will make the equation true. But what if we want to graph the solutions to this inequality? Do you think there's going to be more or less solutions? I think that there's probably going to be more, because the few lessons ago on the number line, we saw that when we were graphing an expression or an equation like x equals 3, there was one solution. But then on the number line, when we graphed x is greater than 3, okay, we went on the number line and we put an open circle at 3 and we shaded everything to represent infinitely many solutions. So let's go ahead and kind of see what happens when we look at two variables. You can see there's a y and an x in this inequality. So what we want to do is we want to go ahead and first start off by regraphing this line. You can see that y equals -2x plus 3 has the same exact numbers as our inequality, but the equal sign has now turned into a greater than or equal to sign. So I'm going to go to my graph and I'm going to plot the value 3. Okay, and then I'm going to go down 2 over 1, down 2 over 1, and then go ahead and make my line. Or I'm just going to kind of leave those, or actually I'll make my line. Okay, here. Let's see how this goes. Here we go. Whoops, I didn't want to do dashed. I wanted to do solid. Okay. There we go. There's my line. So, what we want to do is test some points. Obviously, you're not in teams right now, but we want to test some points to see if they make the inequality true. So let's go ahead and I'm going to just choose the point 0, 0 to begin. And we see that it's not on the line, but let's explore what happens when we replace x and y with 0 and 0. So we are asking ourselves, if I replace y with 0, is 0 greater than or equal to negative 2 times 0 plus 3? I have to plug it in. Now I do the math. Well, I leave the left side alone. Negative 2 times 0 is 0 plus 3. So is 0 greater than or equal to 3? Well, no. If you have $0 and I have $3, I have more money. You don't have more money. Okay, so this is a big no. So this point 0, 0 is not a solution. Okay? Well, if 0, 0 is right here, then I think maybe I want to jump to the other side of the line and check out if maybe those points are solutions. So let's go ahead and try, let's try the point 4, 0. Okay, so we're now asking, is the point 4, 0 a solution to the inequality? So we have, is 0 replaces y, is that greater than or equal to negative 2 times 4, and then plus 3. So is 0 greater than or equal to negative 8 plus 3? Negative 8 plus 3 is negative 5. Is 0 greater than a negative number? The answer is yes. So this point 4, 0 is indeed a solution. Okay? Now, what do you think other solutions might be? Well, let's try another point on that side of the line. So if we go to 2, let's try one without 0. Over 2, up 6. Let's try this point right here. Okay, so we are going to do 2, 6, and we are going to ask, is 6 greater than or equal to negative 2 times 2 plus 3? So we have, is 6 greater than or equal to negative 4? Plus 3. Is 6 greater than or equal to negative 1 when we do the math? Well, yeah, a positive number is greater than a negative number. So 2, 6 is also a solution. Okay. So now the only case, so we kind of can see that the solutions kind of lie here and the not solutions probably lie over here. But what about on the line? Let's pick a point on the line. Let's pick the y-intercept, 3, 0. Okay, so if we take a look and we check, I'm going to do my work up above the graph. We're going to look at, is 3, 0, sorry, not 3, 0, it should be 0, 3, a solution. So is 3 greater than or equal to negative 2 times 0 plus 3? Is 3 greater than or equal, well, negative 2 times 0 crosses out, so is 3 greater than or equal to 3? It certainly is. So this point on the line is also a solution. So it seems that the points on the line are solutions because they are going to be equal. They're going to satisfy the or equal to component. Okay, so now we want to kind of examine, I've already been doing this, but we want to take a look at kind of what's going on here, because we want to, remember, represent the solutions to this inequality ultimately on the graph. But we could sit here for days and we could keep checking points and saying, yes, this works, yep, this works, yep, this works, oh, this works, this works, this works. Okay, so hopefully you're catching on to the concept that there are going to be many, many solutions. So we want to use this graph and we want to answer some of these questions quickly below. Okay, First of all, are there any points that we suspect are indeed solutions but don't have a sticker, okay, or a point? Well, I think I just kind of made that clear by saying, okay, we didn't really check these, but I'm guessing that they're going to work based on the pattern that we saw just simply by doing a few sample points. Okay, if these work, then we're catching on to the pattern that everything to the right of the line and on the line are going to work. So the answer in this case would be yes. And we said it would kind of be everything to the right of the line and on the line. What about the points on the line? Are they solutions to the inequality? What did we say? We said yes, they are, because they make both sides equal, which is going to satisfy the what? The or equal to component of the inequality. Okay, so ultimately, how many solutions are there? Well, like I said, we could be here for days and days and days, but we see that there are infinitely many XY pairs that are solutions. Okay, we could find this process could never end, okay? There are infinitely many points. But the big question is, it's not any point that's going to work, so don't say all real numbers or all solutions, because why aren't any of the solutions located below the line? Well, we saw that the points below the line will make the inequality not true. Okay? It will claim that one side is greater than the other when in reality it's not. So, kind of the big idea of the day, what I've been leading up to, is how are we going to graph these without having to do all of this scratch work? The good news is it's way easier than having to check point after point after point. We are going to use a shading technique. What we're going to do is graph the boundary line using our knowledge of y equals mx plus b. And then we are going to shade the side of the line that includes all of the points that will make it true. So I just shaded the side of the line that has all the points that worked. Now let's go back and see that this inequality uses a what symbol? Uses a greater than symbol. And I'm here to tell you a shortcut that greater than is good. It means go up. So if you look at your boundary line and you draw a line straight up, where do we land anytime we draw those lines straight up? We land in the shaded region. So I am to the point, and you are going to be as well, that you're not going to have to use test points. You're going to understand that greater means straight up from the line, and what do you think less than is going to mean? Straight down from the line. Okay, so let's continue on and kind of do another problem from scratch, because I know I just showed you a lot of work. So what else can we learn about solutions of linear inequalities? Think about this as you answer the questions below. What if the graph were shaded like the one at the right? What inequality would correspond to this graph? Well, we can see it has the same y-intercept and the same slope, I believe. Let's see, down 2 over 1, down 2 over 1, okay, as the last line. So we're still looking at y, I'm going to leave a little space, negative 2x plus 3. But if you notice, they shaded straight down from the line. So are we going to use a greater than symbol? No. All of these points are going to satisfy the inequality that says y is less than or equal to. Because you notice that still the boundary line is shaded. And we're going to talk about that in a second. So the boundary line, notice we used to have a boundary point, but now we have a boundary line, okay? all the points on the boundary line are going to make both sides equal. So this inequality corresponds to this graph right here. It's the opposite of what graph we just worked with. So now the final big idea is, what if I change the inequality to just saying y is less than negative 2x plus 3? Okay, I'm still going to shade below the line, but now when we take away the or equals to, the points on the line on the boundary line are no longer solutions because we don't have the or equal to. So when you don't have the or equal to, how are we going to take care of that? We must use a dashed line or a dotted line. Okay? So the key idea is that when you have, and we'll make some notes here, okay, when you have a less than symbol, it is going to be dashed, and you are going to shade straight down from the boundary line. When you have just a greater than symbol, it is going to be dashed, and you are going to shade straight up from the line. When you have a less than or equal to, it is going to be a solid line because the points on the line will work, but you are going to shade straight down. And when you have a greater than or equal to sign, it is solid, and you are going to shade straight up. Okay? These you kind of have to figure out a way to remember, but it all makes sense when you start applying test points. So these are two problems that would be on a test that I would expect you to be able to kind of come up with the answers relatively quickly. Again, you have to have background knowledge of y equals mx plus b, or else this makes no sense. So what we are asked to do is we are asked to graph the inequalities below, and we need to think about, is the boundary line going to be solid or dashed? And then we need to think about, where do we shade? Okay, so on this first problem, the first thing you're going to do is notice that there's no or equal to, so we have a dashed line. Then next, we see that it is a greater than symbol, so eventually we are going to shade straight up. So let's work on graphing this dashed line by using our knowledge that the y-intercept is -1. Okay, and then our slope is down 1 over 3. It is negative. Whoops, sorry, I'm struggling with my dots. Okay, and then we already established, because it's not or equal to, we need to use a dashed line. So luckily I have my dashed line tool here. Okay, so there is my boundary line showing that none of these points are truly going to make the inequality work. Okay, but then after that, we said the greater than symbol means that we are going to shade straight up. So put your pen on the boundary line and go straight in the upward direction, and that shows you which of the two regions to shade. So then I can get out my pencil, or a lot of people like to use highlighters, and shade this region, and there is our answer. Every single point in this region, these XY pairs, whether they're decimals, a combination of negatives and positives, will make the original inequality true when you plug it in and do the math. Okay, the final problem of the day, we see right away that it's or equal to, so we are going to have a solid line. And then we see it's less than, so we are going to shade straight down after we have our boundary line. So I'm going to start at 2, and then I'm going to go up 4 over 1, up 4 over 1. Now I need to get my ruler and solid line in this case. So I'm going to make my line okay, and then we already said, now be careful, don't ever memorize left and right. We said in order to figure out where to shade, put your pen on the boundary line and just strike your pencil straight down. Anywhere you go, straight down. So what's the shaded region in this case going to be? It's going to be over on this side. So you are going to shade this entire region and know that it extends forever in all directions. So the moral of the story is any point in the shaded region, all of these points will make this inequality true. Okay, so I really want you to focus on practicing these if they come up in your homework, and we're going to continue with this idea of graphing two variable inequalities the next few days. Keep up the good work and let me know if you have questions.